So it's a three-dimensional art exhibit that are these cones that stick out, but everything has been done in linear perspective, so this is the way it really looks, right? So that when you are in front of it, it actually looks like you're looking down the hallway at these paintings down the hallway, sort of thing. It's really pretty cool. I think it's cool. So we're going to talk all about depth perception and depth perception. That's all we're going to talk about today. We got a lot to do. So, questions? We're good? Who usually sits over there?
Shelby.
Shelby, that's right. Just to make sure who's where. Thank you. Okay. No questions, we're ready to go. It's almost the weekend, right? All right, so here are my kids. They would kill me if they knew I'm showing you this picture. Because Taylor's a sophomore in college now, Jen's a senior in high school. But, you know, we took them to, I think it was Walmart or whatever, to get their portrait done. So they're not obviously at the beach, right? So what are the depth cues that when we're looking at this? Like, how do you know, like, is there a sense of depth with this portrait? Yes, I was just yes. Why?
I guess the objects or like the scenes within the picture are kind of layered in a way, like the sunset or ocean is further in the background than the tree is. The same.
Yeah, so that's one of the principal aspects of depth perception is occlusion, right? So the objects that are closest are covering up the objects that are further back, right? And so this is just a backdrop, right? I mean, there's no real beach there, right? But it's painted so that the stair rail, right, covers up the beach, that and this covers up the beach, so therefore this is closer than this, right? In front of that. And so we're doing, like what we talked about last time, figure ground separation, right? What are the figures, what is the background, that sort of thing, right? And there's a whole lot of other cues in here that we're going to talk about that helps us sort of know. And all of these cues, we're going to make a distinction between pictorial cues that are in a picture that are two-dimensional versus three-dimensional cues that we're going to get in terms of our binocular vision, which is going to be different. And I can't demonstrate that here because this is not three-dimensional, right? And you can demonstrate with me because I'm three-dimensional. Okay. All right, so we use a whole bunch of cues or heuristics, right, in order to understand depth perception. Occlusion, as you mentioned, is one of the very first things, cue heuristics that we learn. And in fact, babies learn occlusion by about 5 months of age. It takes about 5 months for them to learn. And you say, well, how can you know that they learn occlusion? Because you present them with items and they grab the top item and not the bottom item, because they've learned that the top item is the top item because it's including the other things, right? Prior to that, they'll grab for whatever because they don't understand occlusion, right? All right, so all of these are what we call monocular or pictorial cues because you only need one eye to see them, right? They don't involve binocular vision. So, I mean, there are two ways you can think about it. You only need one eye to see these cues, or they can be reproduced in 2 dimensions, right? Because you don't need binocular cues, right? Pictorial cues. All right, this is an embarrassing picture. All right, so which one of the 3 men is closer? Left, right, or left, middle, or right? Right. Okay. Which one of the 3 clouds is closer? Left, middle, or right? Okay, why? Why are you saying that? Okay, so size matters, but this could just be a small cloud, right? But you're saying that they probably are all the same size. So if something is the same size and bigger, appears bigger, perception bigger, it must be closer, right? What about these, the man standing there? Does size affect that?
Based on the horizon.
Based on the horizon, yes. So objects that are further away from the horizon appear closer, right? So this is what we call relative height to the horizon, and actually objects above the horizon that appear closer to the horizon and further away. Which is one of the reasons I wish these clouds were all the same size. I didn't create this picture. But if the clouds were all the same size, you still would think that this one's closer because it's further away from the horizon. Right? So the horizon matters. If you're below the horizon, the lower you are, the closer you are. Again, these are heuristics. How do you know this? Why do you think that? Experience. Because in the real world, when you go outside, things that are actually closer to you are further away from the horizon than things that are further away. Right? No one ever taught you that, right? They didn't sit you down to learn your ABCs and whether things are closer from the horizon, but your general experience subconsciously encodes this heuristic. Okay. So, which of the rabbits is closest? Right? The one furthest away, that is lowest in the picture, appears closer, right? Which of the rabbits is the biggest? They're all the same size. All right, is this rabbit bigger than this rabbit? Right? If this rabbit is further away than this rabbit, yes, you perceive that as bigger. In reality, right, that rabbit and that rabbit are exactly the same size, right? The depth and size are integrally linked together. The closer things are to you, the bigger they appear. The further things are away, the smaller they appear. And when we have a picture like this, all these rabbits are appearing the same size, right? It doesn't create depth perception, right? It feels odd. This feels weird, right? It feels like someone drew that line. All right. Here's another example.
Hey, Vsauce. This is called the Dolly zoom effect, and the optics that make it possible are also responsible for what's called the moon terminator illusion. A terminator is the line between an illuminated and dark side. Light arrives perpendicular to the terminator, but it doesn't always appear to. Maybe you've noticed this before. When the moon and the sun are up at the same time and a good distance apart in the sky, the direction the moon is being lit from won't always appear to line up with the position of the sun. What's going on here? The answer lies in visual angles. The further away from you something is, the smaller it will appear to be. In psychophysical terms, its visual angle shrinks, the angle within your field of view that it stretches across. Now, this means that everything we look at is foreshortened. That is, it diminishes in size towards the horizon line, a line infinitely far away. Things that far away are foreshortened in a point which they have no height whatsoever. This distortion affects everything that we look at, but it doesn't confuse us because our brains know about it. We can look at an object that is foreshortened and figure out what it probably actually looks like. For example, a door is a rectangle, but it's wrecked by foreshortening when open. Closer distances appear larger. The whole shape is different, but your brain isn't freaked out every time a door opens because it understands that different sensations don't necessarily mean different actual things. It's called subjective constancy.
You want to know why running on the treadmill 7 days a week doesn't work for you when you're trying to lose weight? Because it never.
Our brains cleverly factor in previous experiences and perspective cues from the surrounding world to calculate in real time whether changes in what we sense are because of actual changes in the things we're looking at, or are just merely products of their positions or the surroundings. For example, I, right now on this video screen, am vulnerable to foreshortening, but I probably look okay to you. However, if we frame in really closely and remove surrounding perspective clues, I can be made to look weird, strange, a little scary, distended. I'm foreshortened without the necessary tools around me for you to mentally adjust. This is probably the crux of the Moon Terminator illusion.
Take a look at this. The line where that wall meets the ceiling is a straight line. Seriously, take a look. If you look to the left and right, it continues to look straight. And trust me, this building was built with level, straight ceilings, but that's not what your eye senses. A camera will help demonstrate this. It doesn't add in the post-sensation processing that our brains do, and we can also frame in to remove other clues telling us what to think. Now, sure enough, right in front of us, the line is level with the screen of the camera. It's a straight line, but if we move our eyes across the line, look what happens. If I pan this way, the slope changes, and now the line appears to be going up and to the left. And if I pan this way, the line appears to be moving up and to the right.
Yet our brain is
What's going
correcting
on
all
here?
that.
A straight line can't have changing slope. That's what a curved line does.
It knows that the ceiling is
Just
straight
like the
across.
curve we think we see between the sun and the moon. But wait, if the line between the sun and the moon is curved because of foreshortening, why don't we see lines like this one as curves? Well, here's a clue. Clues. We know what rooms are supposed to look like. We know how they're built. We have experience with them. And there are other things in the environment helping us. But when you look at the sky, there's not much to help you.
In the absence of clues about distance and perspective, our brains assume that whatever we're looking at is equidistant from us, making the sky a sort of dome surface, like a planetarium screen. Our brains do the
We'll talk
opposite.
about
They
the
assume and
moon
consider
illusion
shortening even
and-
when it isn't really there. Like in this illusion, where the cars seem to be different sizes, but in actuality on the page are all the same size. Everything else in the image is affected by foreshortening, so our brains assume that the cars are too, and decide that in order for them all to have the same visual angle, which they do, the more distant ones must be literally larger in real life. The rate at which the visual angle of something you are looking at changes as you move toward it or away from it is not constant. In order to cut the visual angle of an object in half, its distance.
All right, we don't need to know the physics behind this. But I do want to point out, particularly here, the point of that is two things. Foreshortening, right, is this effect that happens that our brain is constantly accounting for, right? And when things don't match up, right, we reconcile that by changing the perceived size of those images. So this car appears a lot bigger than this car, right? Because in the world, what makes more sense? That there's no foreshortening, or that this is just a really big car? Even though that's kind of weird, having a big car there makes more sense to our brain than foreshortening not being in play, when everything else is foreshortened in this picture. Even though, if you measure this, measure it, right? But just like they move that, these are all actually identical in size. And when you get this slide, you can actually measure, right? And we're going to measure the table. All right, so more binocular cues, right? So here, which of these objects is in the front? The one on the left, middle, or right? Okay, Okay, what are the cues that tell you that? Right, so we have occlusion, right, and we have the placement of the bases, right? That's called relative height. Now, what about here?
Right.
The right, because occlusion wins. Does it feel right? Does it feel like someone drew that picture incorrectly? Because the relative height should match up. If this is in front, then this should match up with the relative height. We can resolve that, right, by just putting a shadow down here, and then all of a sudden you're like, oh, I don't know why it's floating, but clearly that's floating there in front of that, right? So in the real world, this doesn't happen, right? You would always have some kind of other cue in order to know why this is happening. And when we don't have that, our brain looks at it and says, that's impossible, that can't happen. Right? All right, so which one of these individuals is in the fourth one? I mean, is closer to the left, the woman, or the man? The man, based on what? Based on relative height, right? Shoes are closer to us. What about now? Right? They're beside each other because we've added a shadow, right? Okay. Relative size also plays a role in, with our experience with objects, knowing what their perceived size should be, right? So here we have a golf ball, a baseball, and a basketball, all of which on our retina have exactly the same size. Right? But because we know a basketball is way bigger than a golf ball, we interpret it as being further away. Right? Good on that? Okay. So, again, here, this object is bigger than this object. Therefore, we interpret that as being closer, even though it's higher in the data, even though it's higher in terms of relative height. So, our brains are constantly looking at the cues that we're getting and making judgments about what is the most reasonable one to rely on. Right? I mean, this could be a miniature golf ball sized basketball, which would put it right here in terms of our depth perception, right? But because we don't anticipate that's what it is, we anticipate we're further away. If it's the same retinal size as something that's much smaller. All right. Other binocular cues, more embarrassing pictures of my kids, right? So here we are at the Varsity in downtown Atlanta. If you haven't ever been to the Varsity, you should go there. It's a lot of really good hamburgers. But what do you notice about the objects in the background? How far away is this building? Far? Why? It's not right across the street from the Varsity? It's got like a bluish tint to it, right? Because there's a lot of smog in downtown Atlanta. And there's a lot of stuff in the atmosphere. It's not literally miles away. It's probably just a couple blocks away. But we call this atmospheric perspective. And so down here, right, again, there's some kind of depth perception here, but it still looks weird with these triangles. But as soon as we make some of the triangles in the back fade, we now gain relative height and aerial perspective, and they appear to have depth and be further away than the ones that are right in front. What else do you notice about this building? What's another clue besides the fact that it has that amount of atmosphere in it? Yeah?
The trees overlap on top of it in regards to the building contours.
Yeah, so we're saying, okay, I know what a minivan size is, and I know that a tree is about that size, right? This looks like several-story building, right? It's not a miniature building right behind the trees, right? So we're using our knowledge of that and the details. Like, can you see details on this building? Like you can see on the cars? No. So the further away something is, the less acuity we have, the less details we get, in addition to having the aerial atmospheric distance. So we have some, but that doesn't help us here, right? We can't use those same cues to know how far in front of this tree is this mini-man, right? So different depth cues may work for different distances. Aerial perspective only works for far away distances, doesn't work for close distances. Okay. All right. Again, back to foreshortening, one of the things about foreshortening is linear perspective. So again, pictorial cues, one of the cues that this is further away than the people in the foreground is the fact that it's higher and that these lines converge towards it, towards the door, like a horizon. Also, again, we have texture. Here we can see the tiles. What happens to the tiles the further away they get? You lose that detail, right? And so what separates my drawing of my artwork from a professional artist's work is I don't really know how to do this very well. And so when I draw it, it looks like a kindergartner drew it. I mean, you don't have that same perspective. You're not able to do it in the same proportions as would happen in reality. The closer you are to mimicking the proportions in reality, the more lifelike or realistic the picture becomes. Again, this is part of the Ponzo illusion that I'll ask you to look at in your book. But you know, these railroad ties are the same size here as they are here, even though on our retina they're much, much smaller, right? So we perceive them. So again, we know, hey, the train tracks aren't coming to a point and getting smaller. Therefore, since the size is constant, what must be changing? The distance, the depth, right? So if size is constant, but if we know the size is constant, but our perception of size is getting smaller, we have to compensate by saying it must be further away. Same thing here, this appears to have depth because the lines get more dense and smaller, and there's a horizon that they're approaching. So therefore we get that perspective of depth. Texture gradients provide us information about how far away something is, right? And if we remove that texture gradient, so if I'm here, I can sort of judge where it's 5 feet by how the carpet changes, right? But if someone takes that away and makes a pit like this, right, we tend to overestimate the distance. Why would that be important? Or why would we overestimate? Safety, right? So if I'm going to jump across this pit, right, do I want to overestimate how far I need to jump or underestimate? Right? So there's some pressure, right? We take that away and we get overestimation. So here, if there's a no gap, we're really good at knowing that's the target distance. If we now ask people to judge how far away something is and we put a gap there, all of a sudden they judge that distance to be much further. Because from an evolutionary standpoint, when we were out trying to survive, the people that overestimated jumping across something survived, the people that underestimated didn't. That becomes a heuristic that becomes important to our survival. Not so important today necessarily, right? But over a long period of time it was. All right. So all of that, all of what I've talked about so far, you only need one eye to do. It's all binocular. It can all be demonstrated on the board, right? We have motion-produced cues. I mentioned this, I think, last time. Motion parallax. The objects that are closer to us appear to move faster than objects that are far away, right? And so think about it. If you're in a train or more likely in a car, right, coming down the interstate, and you're looking at the farmhouse or the tree way over there, and you're looking, and then there's things closer to the road, right? Things close to the road are going by really fast, and the house is just sort of traveling along in the distance very slowly. This is called motion parallax, and it happens because of the amount of distance that this flower is moving across our retina in the same period of time that something far away doesn't move that far. So here, let's look at it this way. So if we start out, and we're going to move our eye from position 1 to position 2, and A is close to us, and B is far away. This is where they are on the retina, right? And we're going to move over here. A moved that far, right? And B only moved that far. So our perception of that is that A is traveling a lot faster, right? And if we say that A moves 6 centimeters in 1 second, B only moved 2 centimeters in 1 second, that's speed, right? A lot faster, 6 centimeters a second versus 2 centimeters. That's why things appear, motion parallax, things that are closer appear to move faster than things that are far away. Even though they're not moving at all, we're the thing that's moving at a constant speed. Good? I mean, if this gets confusing, stop it. We'll talk about it. All right. Another thing, we talk about accretion and deletion. So my little yellow guy here, right? We know that he's walking down the pathway here and is in front of these trees and in front of that curve because of accretion and deletion. Because the foot is deleting parts and other parts are being created when it moves. And if I put another one, like giant red guy walking back here, right, we know that it's behind the tree that's walking down this sidewalk because it's not accreting and deleting that. Right? So accretion and deletion are 2 cues that we use for knowing where things are. The same sort of thing, they use the same sort of thing with like green screen and film, right? Because the person, they have things moving behind you and things are getting accreted and deleted by the thing that's in front of the green screen. Therefore, it gives an illusion of this depth perception. Yes, Dave?
Do these need bypass, or are these still only need one eye?
Only need one eye, right? You close one eye and it still works, right? All of these are binocular cues. Motion parallax, you close one eye and still that one thing's moving faster than the other. Okay? All right. Now, two others. Ocular motor cues. Okay? And actually, well, you'll notice kind of tricky. But you can close one eye and you still have the same. So, everybody, put one index finger as far away from you as you can, and put the other one about 3 inches from your nose. Focus on the one that's far away. Okay? Now focus on the one that's close. What happened to your eyes? Now focus on far away. Feel what's happening motor-wise with your eyes. Now focus on what's close. Okay? Focus on what's far away. All right? That movement is called, well, we're doing 2 things. One, the thing you're not really feeling is that lens in your eye is contracting to keep it in focus. It's called accommodation. We talked about that when we talked about how vision works way back when, a couple of weeks ago, right? And we have convergence of the eyes, right? The greater the convergence of the eyes, the closer our focal point is, right? Which we're going to call a horopter in a minute. But our horopter, we can move that by converging our eyes or our plane of focus, if you will. All right? And the other thing, so you can really feel the movement of your eyes. The other thing that's harder for you to sense or detect is the contraction of the lens in terms of accommodation. That's happening as well. All right? As we get older, harder to do accommodation, so we hold the menu way out here, as far away from us, because we can't do that. We can still do convergence. It's the accommodation that becomes more difficult while we need reading glasses. All right. So again, aerial perspective, not happening here, right? But for cues really close into us, we have another cue, which is the ocular motor. After you get about, I think it's 20 feet away, your eyes aren't moving or doing any convergence or accommodation. It's So we have to align other cues other than this cue. It's only good for short distances. All right, binocular vision. We have two eyes. They overlap. But they give us a different visual angle because they're separated by a couple of inches on our face. Okay? This thing gives us a different angle of perspective for each thing. All right, so the difference between these things is called binocular disparity. So here's a picture that was taken with two lenses as if they were your eyes, right? Separated about the same distance apart, and what do you see is different in the pictures? Like the person in front is occluding different things in each image, right? So here you can see this part of the building, but here that part of the building is occluded. Here you can see this part of the helmet, but here it's occluded. Right? So our eyes are actually seeing, because they're not on top of each other, are seeing two different things. And you can do that, right? If you kind of go back and forth, or close your eyes back and forth, and look at me, I'm kind of shifting back and forth as you do that. Because you're separating those two images out when you do that. I don't want to make this go on weird stuff. But yeah, I mean, you can actually experience this, right? So, I meant to bring my viewfinder. So I have a viewfinder for my kids, right? You ever have these little viewfinders and you look and you see a 3D image and it looks really three-dimensional? I'll bring it next time. I have it on this, right? I'll have a little synthesizer. Same. But, so I have a Thomas the Train viewfinder and it looks 3D, and if you pull the disc out and look at the two images, which is what I did here, right? It's creating binocular disparity. The distance between the telephone pole is different, right? The tracks, what you see is different. And by having those stereogenesis line up, right, it creates a three-dimensional effect in each eye. Because you're projecting one to each eye when you look through the viewfinder. All right. So this is an example. That's what we would call a stereoscope, where you have two images, and this works better in the book. It's harder to do on the screen, but you can create, if you can fuse these images, and if you get them on what we call corresponding retinal points by focusing your plane of view. And we'll talk about, have you ever seen some magic eye things where it's like a random dot stereogram, where it's just like, if you just look at it, it looks like randomness. But if you stare into it, you see three-dimensional objects, but you have to adjust your plane of focus to get those things on what we call corresponding retinal points. I'll talk about this more in just a second, right? So the random dot stereograms are creating depth in the same way. All right. Yes. Great. So size and depth are linked together. Now, what happens if we eliminate the ability to perceive one another? So we eliminate the ability to perceive depth, right? It's what we call in like whiteout conditions, where there's either clouds or snow or something that's preventing us from seeing how far away something is, right? Then, in this case, a helicopter, right, could think that a small image on the ground is actually a dump truck, and that the helicopter is actually further above the ground than it actually is. So the point of this is when we can't tell if that's a toy truck or a real truck, right? Or, so we can't judge the relative size, or we can't judge the relative distance, things become tricky. Right? We're not able to do that perception correctly. All of this is because of that visual angle they were talking about in the video we saw. Because this creates the same visual angle as something that's far away. What else did we call that last time? Called it a problem. Did we study that in the last section?
I did, but
The correspondence problem, right? Call that the correspondence problem, right? The fact that we can have multiple things create the same image on our retina is a problem for computers Why did we say it wasn't a problem for us? Isn't as big a problem for us. Top-down processing, and we said that movement, right? So just a little bit of movement of our eyes, and we get motion parallax, and this thing will move more than this thing, and we know now that this must be behind us. Right? And also movement of our eyes can take those things out of the same visual angle and create occlusion. Right? All right. So what is the perceived size of the sun and the moon? You look up in the sky. Do they look the same size? How many people saw the eclipse? Like when we were all in high school when the eclipse happened? Like, I'll be talking about this in a couple years ago. Were you in middle school when the eclipse happened? Right? What happens in the eclipse? They line up, and the moon covers up the sun. So are they the same size? Perceived size, yes, right? I mean, if the moon can cover the sun, it's got to be the same size, right? Right? So in an eclipse, right, the moon covers the sun, same size, right? But in reality, are they? Why? The distance, right? But we don't have a perception of 93 million miles, right? 93 million miles is a long way away. That's how far away the sun is, right? The moon's a long way away too, at 245,000 miles, right? A 250,000 miles. But it's a lot closer than the sun. So when they appear the same size, the moon is way smaller, 2,200 miles across compared to the sun because of that distance. But when we look up in the sky, we have no depth cue, we have no heuristics, no depth cues to tell us like one is infinitely further away than the other. So they appear the same size. All right. So is the moon ever appear bigger? Right? So when does it appear bigger? When have you seen a really big moon? The harvest moon, right? And so was that on the horizon or up in the sky? On the horizon, right? So we do in our orbits like get occasionally closer and further away from the moon, but closer in terms of not hundreds of thousands of miles closer, right? So why does this moon, right, appear smaller than this moon, even though if I pull this over here, right, they're exactly the same size, right? Because we have depth cues here of this mountain, the trees, and how big this is that we don't have when the moon is far up in the sky without it. So, again, here, moon looks small, here, moon looks big. This can happen in the course of a night. See, I'm going to make you be geeks. So next time you see the moon on the horizon, I want you to be like, wow, the moon looks really big. The next time you see the moon and you say, it looks really big, take a picture of it with your phone, right? And then the next time it's up in that sky, take another picture of it. If you measure those images, if you don't zoom in or anything with your camera, and you measure, they will physically, on both of those images, be exactly the same size, even though you perceive the one on the horizon as being much bigger than the one up in the sky. Right? All right. So, while the moon can change size a little bit in Jupiter orbits, not as drastically as when you see that huge moon on the horizon. Right? This is called the flattened heavens illusion. And it's the fact that when something is on the horizon, all these other cues are helping us judge how far away it is. And if something is the same size and far away, then we know its real size must be much bigger. Well, so, anyways, that's perspective. All right. So we have, if we have depth perception, right, then we can judge, even though the retinal size is changing, if if we know the actual relative size, then we can judge that, that relationship between size and distance. And it turns out there's an equation for that, right, which says that your perceived size, right, is a proportion of the retinal image and our perceived distance. Our perceived distance. So as this number goes up, distance goes up, what happens to the size on our retina? It's smaller, right? And that proportion stays constant so that our perception of that object doesn't change. You hold a quarter right in front of your face, it's a huge retinal image. You hold it way over here, it's a small retinal image. But because of the perceived distance, the change in that compensates. And so we keep our perception of size constant.
So how is it like with mirrors, it throws off like you know, like if your car rear mirrors, like objects maybe closer, that's like a refraction of the rest of it, or just?
Yes. So the way that that's reflected, right, it may appear further away. They may actually be closer than that distance because of the reflection of that mirror. Because mirrors don't replicate distance very well, depth very well. All right. So how big is this wagon wheel? How big are wagon wheels? Like what? Here? Like shorter than me? Right? Well, how big's the wagon? Right? So we use familiar objects to judge size. So now, if I show you this, how big is that wagon wheel? How tall is a woman, right? We're assuming it's an average-sized woman and not a necessarily small woman, right? So given that, we're looking at like, I don't know, 20 feet or 15 feet, something like that. It's twice her size, right? 10 feet. I'm like, that's a parable.
That's a little much.
Little exaggeration. But way larger, right? I take that away, and now we're like, okay, how do I judge that? Well, I'm thinking about my experience, like what are normal wheels like? What size are normal wheels? Right? Probably not that big. Right? All right.
Does what we see correspond to what's really out there? Or does our brain construct its own version of reality? One that does not always match up with the physical universe. Check me out, for example. I am the same size here as I am over here. But over here, I look much larger. No, it's not a cheap video trick. It's a trick on your brain. Here's what you're seeing. The me over here is indeed projecting a smaller image onto your retina, the region of light detecting cells at the back of your eye. All else being equal, smaller images mean smaller things. Here, I'm in no danger of hitting my head on the ceiling. But over here, I am ducking. Ceilings are useful visual landmarks for judging size. Of course, you're making these size estimates based on the assumption that this room is ordinary and box-shaped. You assume the back wall is perpendicular to the line of sight, so the two versions of me are the same distance away. You're also assuming that the floor and ceiling are level and parallel. But as you probably guessed, this isn't the case, and the room isn't box-shaped at all. It's trapezoidal. The back left corner of the room is much farther away than the right. Since I'm farther away over here, my image is smaller, although I'm definitely not. The ceiling cue is also misleading. The floor actually slants upward and the ceiling downward from left to right, making my head much closer to the ceiling when I'm over here. Why couldn't you see these things and adjust your size estimates? The room's features have been cleverly distorted to be consistent with a rectangular shape. The checkerboard pattern on the floor gets finer grained toward the right, so that the same number of pattern elements fit in a shorter distance. The windows are resized and shaped to match the trapezoidal back wall. Your narrow angle of view from the front of the room blocks the cues that would reveal
So
the
as soon
room's
as they
true
get
shape.
close enough to
And of
reveal
course,
these
we
cues,
easily
they just
believe
know.
in a box shape because that's the shape rooms normally are. This clever setup is called the Ames illusion. American ophthalmologist Adelbert Ames Jr. devised it in 1934 and built a physical example the following year. For Scientific American's Instant Egghead, I'm Ingrid Wiggleman.
All right. So again, if we think about this, right? If our depth perception is constant, right? Yet here, our retinal size is 3, and here our retinal size is 5, right? Then our perceived size is that this is much smaller and this person is much bigger. Y'all get that? How this equation shows you how this Ames room works? Cool. All right. Now we get to talk about the complicated stuff. That was easy. Now we get to talk about its corresponding retinal points in binocular discovery. Okay? So the distance, our brain calculates, is able to actually calculate the distance between two objects, the same objects, in each of our eyes and compare them. Right? And when that distance is not equal, right, then it says that those things are at different depths. So here, and we can actually do this to, we can calculate that difference to the level of 1 micrometer on our retina, which is pretty amazing because our receptors aren't even that small. So here, if we move point D, so here, the distance between A and B is different in the left eye and right eye because it's further away. If we move point B up here, now it becomes equidistant. And now these are the same distance apart. And our brain says, hey, those two things are next to each other, not at different depths. All right. So this blue line, this line of focus out here is not a straight line. Why isn't it a straight line? Why is our plane of focus line? If I tell you it's a curved line, why would you think that would be the case? Because what? Because where is that? Where is this image being projected? Is it being projected on a straight line? No, our retina is curved, right? So that creates this curved plane of focus because our retina is the sphere, right? All right. So this plane of focus is actually, I mean, these points are pretty close together, so it could look like a straight line, but if we get further over here to stay in that plane of focus, which we call the rota, it has to be on that curved line, right? So here, the lifeguard watching the kids in the pool, and she's looking at Ralph, Susan and Harry are on the same, are in the plane of focus, right? Even though they're not next to each other, right? It's also called a Binocular circle, but we're going to call it rota because that's easier to say. So when something's on the rota, Susan, Ralph, and Harry, they are following on what we call corresponding retinal points. So this point here on the retina, point A, corresponds with this point here, A prime. And F and G match up, right? And if we put somebody here, right, they're going to fall on, say, B, but over here they're going to fall on E. And they're not going to be on corresponding retinal points, and so it's not going to optimally.
And so those people appear to be in a straight line? Because
Well, they don't appear to be in a straight line because our brain knows the rotor's curved. Right? And so it knows. But those people appear as one image in our brain. So we also can call this horopter as a plane of focus or fused images. And so when we're focusing our horopter here and things are falling on corresponding retinal points, those are corresponding retinal points because those are the points of the retina that match up in the LGN and go as a single image from our left and right eye to our brain. All right, I'm going to show you this again. Stick your left hand as far away, right hand up close. Look at your left hand. Okay? When you look at your left hand, how many fingers are on your right? You see one or two fingers on your right hand if you're looking at your left. I hope you say two. Focus on your right hand. How many of your left hand do you see? Two, right? That's because you're changing the horopter. And when you're outside this plane of fused images, you're falling on non-corresponding retinal points. They don't match up in your brain, therefore we see two images. You want to do it again? It's kind of cool, right? Look at your right hand. Move your left hand out there. There are two. If you stay focused, right? You have two fingers, two arms. Focus on your far away one. Again, the close one. There are two because it's falling on non-corresponding retinal points. Or less impressed than I am. Right? And so that results in what we call diplopia, or double vision. We see two images because they're not hitting the places on the retina that match up. That's hardwired. And that doesn't change. We can change where our horopter is by moving our eyes, converging and accommodating our eyes, right? But those points, those corresponding retinal points are hardwired to the same area in the retina. If we put something on non-corresponding retinal points, there become two of them. All right. So this again, trying to show you that in the horopter, those are falling on F and B, and the corresponding points are F and B over here. But if something that's close in is going to fall on C and E, non-corresponding, they're not going to, so F and B, these are the things that match up in the LGN to form a single image. But C and E don't match up. They go to two different places, so we see two of those. Same thing if it's behind the horopter. All right. This is Bob and this is Floating Crayons. This is from your book about relative disparity. They try to show you this. So if red is on your fovea in a single image, right, and brown and purple are not, the distance, right, between there is different. So that these are actually falling on non-corresponding retinal points. However, blue is in our plane of focus. It remains the same distance, right? Brown is not, so brown is a different distance as well. Good. And then this is a little complex point, right? So, how different this is? Brown is not very different, right? Purple is way different than brown. We interpret this difference as this thing is further away from our horopter than this thing. The closer it is to our horopter, the more it comes together until it's actually in our plane of focus and becomes a single thing. The further away it is from our plane of focus, the more disparity there is in between those two images on our two retinas. Good? Okay. You want to make it even trickier? Think about this. Your horopter's not fixed, right? You can move that plane of focus in and out, just like you switched it back and forth between being close and far away with convergence and accommodation. Right? So it gets really kind of complicated. All right. So relative disparity, the bigger the disparity, the further from the horopter. Now, there's another clue that helps us know if that disparity is happening because it's in front of our horopter or behind our horopter. In front of our plane of focus or behind our plane of focus. And that's called cross and uncrossed disparity. And so when it's crossed, meaning it crosses here, which actually the weird thing is in our brain it looks like it's on the inside. that disparity, if it's crossed, means that the thing is in front of our rotor. And if it's uncrossed on the inside medial portions, then that means it's behind our rotor. And we can act, and no one sat you down and taught you, hey, I mean, you can't even perceive this, right? You just learn it, and it becomes a cue for depth perception subconsciously, because it's always present in our environment. Yes?
But can't depth perception be trained?
Trained?
Like, don't you think that, like, over time you get better at, like, perceiving, like, speed or depth? Like, I think about, like, an athlete who has to do more with gauging, like, how fast or far away than someone who has no experience.
Sure. I mean, so all you're doing there is increasing your experience, right? So you're not actually, like, cognitively learning something, you're just practicing it so much that you're getting more cues that you're gaining more. Like, if I've never driven a race car at 200 miles an hour around a racetrack, I'm going to have a hard time judging depth between other objects than if I'm a NASCAR driver and I've done this all my life, right? Because I've put that input in my brain, whereas someone who hasn't done that doesn't have that same, but could learn it if they had enough experience. Sure.
So, like, hypothetically, if somebody was only experienced, like, maybe on, like, trapezoidal rims, or, like, everything was just off.
Like we put the cat, right, in the thing with only vertical lines, and you don't develop that. So we talk about how angles of lines, you could have the same thing with depth, but that would be a very odd environment for a line, right? Okay. All right. Other examples here, sort of showing you, when we're at the zero disparity, that means we're on the plane of focus and we're hitting corresponding retinal points. Anything that's not our plane of focus is falling on non-corresponding retinal points. Right? And if it's cross disparity, right, then that thing is closer to us. And if it's uncrossed, that thing is further away. And again, the crazy thing is like we can change our plane of focus. So now here, both of them become crossed. Because they're both in front. Or here, both of them become uncrossed. They didn't move, we just changed where our plane of focus was. Right? When these are on non-corresponding retinal points, how does that appear to our brain? What happened to your fingers when they were not on corresponding retinal points? Diplopia, right? You see two of them. Are you constantly, things that are on your plane of focus, seeing two? Like I'm looking at Gibson right now, but I'm not seeing two of the people behind them, right? So our brain is sort of filtering out and saying, only like process the stuff that's coming in perceptually to be that's in our plane of focus. That other stuff is just not in our plane of focus. It's not two of them, it's just not in our plane of focus. Alright, so a lot of this is perceptual, psychophysical stuff that we know. And it's harder to find physiological evidence of this because it's hard to find a research model to do this. Like, how can you get like a cat or a monkey or some animal that has pretty good visual acuity to change their depth perception and change where their rotor is on command so that we can measure cells in the brain? I mean, this is a technologically difficult thing to try and do, right? But we can find evidence of zero disparity cells and non-disparity cells in the brain. And so there are cells that have tuning curves that fire when something is at zero disparity, and as the disparity gets bigger, right, the firing goes down. It's less likely to fire. And that's actually a good thing because what's happening when this goes down? We're seeing two of that image, right? So our brain sort of shuts down that diplopia perception of non-zero disparity, non-zero corresponding retinal points. No, that's not one point. Sorry. Okay. So we can find tuning curves for disparity in V2, V1, V2, and MT pathways and in the ventral pathway. It's helping us identify objects and suppress inappropriate objects. All right. So this is an example of cells that would actually fire. We could see a red cell that's going to fire for the cross disparity, and another cell that fires for uncrossed disparity. Again, these are some more examples of cells that fire for zero disparity and cells that fire for non-corresponding retinal focus. Because something's not magnetic focus. All right. So this again gets sort of back to the correspondence problem, like how do we know where something is if we're moving our rotor and changing what's on corresponding and non-corresponding retinal points, right? And so we're trying to interpret this by knowing how much our eyes converge, right? Am I looking at something close or far away? Where's my rotor in that? So, again, we could have 3 dots that form the same image on the retina, but we could also have an illusion that's producing exactly the same stimulation on the retina, but now there are 2 of these things instead of 1. And so this is if it's actually in a 3-dimensional, there are 4 points out here instead of 3. We can do this, we can do the reverse and say it's flat, but we're seeing something that's actually not there. And that's what those random dot stereograms are doing, right? So we have multiple interpretations of the same stimulation. And that's how we can create a 3-dimensional picture from a 2-dimensional image. Good? Okay. All right. So in these random dot stereograms, and again, probably it won't work up here, it works better if you're in front of a computer screen, but there's actually a a rectangle that's similar here, and it's sort of offset in this one. And the way that it's offset is set up in a way that you can have those images falling on non-corresponding retinal points in your plane of focus. But if your plane of focus shifts, it lines them up to create that 3-dimensional image. So that back here, these 2 boxes appear to have a 3-dimensional cube shape, even though if we look at them in our barometer, they don't line up, and so they fall on non-corresponding retinal points, and our brain doesn't perceive them. Just like when I'm looking at you, I'm not perceiving the double vision unless I do a trick like with my eyes and I really focus on it, right? Okay. So you can try this. It won't work here. But you can look at this image, and there's a cone, a sphere, and a cube that are 3-dimensional in this stereogram. And you have to kind of focus your plane of focus in and out. I think all of us do it when we're sitting right here. But the deal is, do this in front of your computer screen, and then cover up one of your eyes and see what happens to the image. You lose the ability to detect it because it's binocular. You have to have both inputs from both eyes in order to trick your brain into them, right? You close one eye, you can't maintain the perception because you're not putting along corresponding retinal points anymore, so you don't perceive. All right. So, different occlusion works no matter how close or far away you are. If something's covering something up, the thing that's covering it up is in front. That's the way the portal works, right? Unless it's an illusion or something. Okay? Relative size works as long as we know how far away something is, right? If we know that people are about the same size and I'm this big on your retina, you know I'm way across campus, right? Other things work for short distances or long distances, right? Longer distances. So again, all of these cues are sort of working together. When they match up, our perception becomes way stronger. When they don't match up, we either ignore the cues so that we have the right perception, or we have a weird perception, like those rabbits should not be the same size if they're at different distances. So here's another summary of sort of what we have. We have oculomotor cues that kind of sit out here by themselves, because they do sort of require two eyes, although, I mean, if I close one eye and I do that thing back and forth, I can still feel my eye moving, even though it's only coming from one input, right? Binocular cues, we have static cues that are pictorial. We have dynamic cues that are in motion, like motion parallax. I'll talk about optic flow next Tuesday, and accretion and deletion. And then we have binocular disparity on top of all that we get from our two different perspectives, with crossed and uncrossed disparity, and following corresponding or non-corresponding rapid points. All right, it's next time. We're not going to go slower and show you more than these last week. Let's worry about it. All right, on your own, look at the Ponzo illusions in the book. All right, after you do that. If you just stare at that, it's cool.